Chapter 1. Introduction to Neural Networks. 1.1 History and Evolution of Neural Networks. The chapter begins by delving into the history and evolution of neural networks, a field that has been influenced by the intertwining of various scientific disciplines, including biology, computer science, mathematics, and psychology. Neural networks, in their most basic conceptualization, are designed to mimic the working of the human brain, promising to overcome tasks that were once thought to be solvable only by human intellect. This foundational idea emerged from the early 20th century as scientists endeavored to understand how the brain's network of neurons processes information. Their structure and function inspired the creation of computational models that attempt to emulate biological neural processing. In the 1940s, the first step towards artificial neural networks was taken with the introduction of the McCulloch-Pitts neuron model. Warren McCulloch, a neuroscientist, and Walter Pitts, a logician, proposed a mathematical abstraction of brain activity that laid the groundwork for future developments. They presented a simplified model where a neuron could be either on or off, depending on the input it received, thus introducing the concept of binary threshold neurons. Although simplistic, this model spurred further interest in research into network structures that could perform complex computations. The 1950s and 1960s witnessed significant advancements in neural network research with the creation of the perceptron by Frank Rosenblatt. This model was based on a single layer of binary threshold neurons and included a simple learning rule for adjusting weights based on the discrepancies between actual and desired outputs. The perceptron was capable of solving linearly separable problems, but it had limitations that were highlighted by Marvin Minsky and Seymour Papert in their book, Perceptrons. They showed that a single-layer perceptron could not solve simple nonlinear problems, a revelation that led to a reduction in funding and interest in neural network research, known as the first AI winter. Despite this setback, the 1970s and 1980s saw a revival of interest in neural networks, thanks in part to the development of the backpropagation algorithm. This algorithm, which facilitates the training of multi-layer neural networks, was independently discovered several times but is most often credited to the work done by David Rumelhart, Geoffrey Hinton, and Ronald Williams in 1986. Backpropagation allows the network to adjust its internal weights based on the error of the output, effectively teaching the network to perform a task. This innovation made it possible to train networks on a much broader array of tasks, as they could now model nonlinear relationships. Parallel to these developments, an alternative approach began gaining traction with John Hopfield's introduction of the Hopfield network in the early 1980s. His work provided a model for associative memory, where patterns could be stored and recalled within a network. The Hopfield network is a form of recurrent neural network with bidirectional connections, which means that information flows both ways between nodes. This model demonstrated how neural networks could be applied to solve optimization and memory problems, and it was notably different from the feed-forward networks the perceptron had created. The 1990s saw a diversification in neural network models with the advent of support vector machines, SVMs, and the resurgence of neural network approaches, such as convolutional neural networks, CNNs, and recurrent neural networks, RNNs. CNNs, developed by Yann LeCun, are particularly well-suited for image recognition tasks due to their hierarchical pattern in image processing, reminiscent of visual perception in biological organisms. Largely regarded as the backbone of contemporary computer vision, CNNs employ techniques such as shared weights and pooling to reduce the complexity of the network while preserving the spatial hierarchy of features. Parallel to the evolution of model architectures, the increase in computational power and the advent of big data in the 21st century have been crucial enablers for the renaissance of neural networks. GPUs, graphics processing units, provided the massive parallel computation capabilities needed to efficiently train large neural networks. Consequently, the field has observed an explosive growth in deep learning, where networks with many hidden layers can learn highly abstract representations of data. This deep architecture is the defining characteristic of modern neural networks, hence the term deep learning. The development of deep learning has led to dramatic improvements in tasks spanning beyond image recognition, including natural language processing, speech recognition, and game playing. In 2012, a pivotal moment occurred when a neural network named AlexNet won the ImageNet Large-Scale Visual Recognition Challenge, beating traditional computer vision models by a significant margin. This success demonstrated that deep neural networks could outperform previous technologies on challenging real-world problems, leading to widespread adoption and investment in the technology across various industry sectors. Today, neural networks continue to advance rapidly, with new architectures and training methods being developed at an accelerating pace. Generative adversarial networks, GANs, which consist of two networks that train together and generate new synthetic instances of data, have pushed the boundaries of unsupervised learning and creativity. On the other hand, reinforcement learning, exemplified by systems like Google DeepMind's AlphaGo, has demonstrated the ability of neural networks to master complex strategies through trial and error, further underscoring their versatility and wide-reaching impact. Overall, the history of neural networks is marked by periods of intense enthusiasm, interspersed with moments of skepticism. Each wave of neural network research has contributed to a deeper understanding of their potential and limitations. Now they are a cornerstone of modern artificial intelligence, providing a powerful tool for diverse applications. As researchers continue to explore the frontiers of neural network design and application, the field stands poised to shape the future of technology and society in profound ways. 1.2 Fundamental Concepts and Terminologies. Neural networks, more formally referred to as artificial neural networks, ANNs, are computing systems inspired by the biological neural networks that constitute animal brains. At their core, neural networks are a collection of connected units or nodes called neurons, which loosely model the neurons in a biological brain. Each connection between neurons can transmit a signal from one neuron to another. The receiving neuron processes the signal, and then signals downstream neurons connected to it. Neural networks rely on a process of learning from observational data and improve their tasks drastically over time, which differentiates them from static program instructions in traditional computing machinery. To understand how neural networks operate, one must first become familiar with their fundamental building blocks, the artificial neurons or nodes. These are simple processors which receive input, process it, and produce output. In the context of a neural network, each neuron takes weighted inputs, sums them up, applies a nonlinear function to the result, and outputs the final value. The weights are adjustable parameters, and the training of a neural network involves finding the right values for these weights, so that for given inputs, the network produces the desired output. The architecture of a neural network refers to the overall design of the network. It includes the pattern of connectivity between nodes, which can be thought of as the network's wiring. The most straightforward architecture is a feed-forward neural network where the information moves in only one direction, forward, from the input nodes through the hidden nodes, if any, and finally to the output nodes. There are no cycles or loops in the network. However, there are also more complex architectures like recurrent neural networks, RNNs, where connections between units form directed cycles, which enables them to use internal state memory to process sequences of inputs. Training a neural network involves adjusting the weights of connections between neurons. This is done by using a set of examples, known as a training dataset. Each example in the dataset has inputs and corresponding desired outputs, and the network's performance is measured using a loss function that compares the actual output of the network to its desired output. During training, the network adjusts its weights in an effort to minimize the loss function, typically through a process known as backpropagation, which updates the weights in proportion to their contribution to the error signal. To further elucidate the training process, the concept of an epoch must be introduced. An epoch is one complete presentation of the dataset to be learned to a learning machine. During an epoch, all the examples from the training set are presented individually to the neural network. For effective training, multiple epochs are usually required. The amount of epochs needed can vary greatly and depend on the complexity of the task, the architecture of the network, and the chosen learning rate. which is a hyperparameter that determines the step size at each iteration while moving toward a minimum of the loss function. Another key concept is the learning rate, a critical hyperparameter that controls the amount to which the weights of the neural network are adjusted during training. A learning rate that is too high can cause the network to converge too quickly to a suboptimal solution, while a learning rate that is too low might result in a long training process that could possibly stall. Finding the right learning rate can be a challenging yet crucial task in training an effective neural network. Activation functions play a central role in determining the output of neural networks. They are applied to the weighted sum of inputs to a neuron and decide whether it should be activated or not. Common activation functions include the sigmoid, 10H, and rectified linear unit, ReLU. These functions introduce nonlinearity to the system, allowing neural networks to learn complex data and perform tasks such as image recognition, speech recognition, and many others. Neural networks can also be categorized based on the number of layers they have. A shallow neural network might just consist of an input and an output layer, perhaps also with one hidden layer. By contrast, deep neural networks have multiple hidden layers. These additional layers allow for the modeling of more complex relationships in the data. Deep learning, a subset of machine learning involving deep neural networks, has gained immense popularity for its ability to process and learn from large amounts of data. Optimization algorithms are utilized to minimize the loss function of the neural network. The most commonly used optimization algorithm is gradient descent, which makes use of the gradient of the loss function to change the network's weights in the right direction. There are several variants of gradient descent, including stochastic gradient descent, SGD, which updates the weights on an example-by-example basis, and mini-batch gradient descent, which updates the weights after computing the gradient of the loss function over a small subset of the training data known as a mini-batch. Lastly, it is crucial to acknowledge that neural networks are not immune to problems such as overfitting, where a model performs well on training data, but fails to generalize to unseen data. Techniques like regularization, dropout, and cross-validation are employed to combat overfitting. Regularization methods such as L1 and L2 regularization add a penalty for higher weights to the loss function. Dropout involves randomly deactivating neurons during training to prevent co-adaptation of features. Cross-validation involves dividing the dataset into a number of subsets and training the model on all but one, which is reserved for validating the model's performance. 1.3 Types of Neural Networks Overview. Neural networks, inspired by the structure and function of the brain, are a subset of machine learning algorithms that are particularly effective at recognizing patterns and making predictions. At the most fundamental level, neural networks consist of layers of interconnected nodes, or neurons, which are designed to mimic the way human neurons process and transmit information. These artificial neurons receive inputs, apply a set of weights that signify the importance of each input, undergo an activation function, and finally output a transformed value. The connectivity pattern between these neurons is key to the various types of neural networks, each suited to different tasks and applications. One of the simplest forms of neural networks is the feed-forward neural network. In these networks, information moves in only one direction, from input nodes through hidden layers to output nodes without any cycles or loops. This structure is straightforward and does not allow for memory of previous inputs, making feed-forward neural networks suitable for mapping a set of inputs to outputs, but less ideal for tasks where historical data is important. Despite their simplicity, they have been successfully applied to a wide array of problems, from speech recognition to medical diagnosis. In contrast, recurrent neural networks, RNNs, are designed to handle sequential data, considering the current input as well as what has been learned from previous inputs. This is achieved by having connections that cycle back into themselves, effectively allowing the network to retain a form of memory. RNNs have been crucial for applications that require the understanding of sequences, such as language translation and time series analysis. However, RNNs can become complex and difficult to train due to issues such as vanishing or exploding gradients, which are problems related to the method of updating the weights in a network during training. To manage these difficulties, variants of RNNs like long short-term memory, LSTM networks, and gated recurrent units, GRU, have been developed. LSTMs include a memory cell that can maintain information in memory for long periods, and gates that regulate the flow of information into and out of the cell, thus mitigating the vanishing gradient problem. GRUs simplify the LSTM architecture by combining the gates into a single update gate. Both of these architectures have greatly improved the performance of RNNs on tasks requiring long-term dependencies, reinforcing the importance of specialized network structures for complex tasks. Another significant architecture is the convolutional neural network, CNN, predominantly used in image recognition and processing tasks. The CNN's strength lies in its ability to automatically and adaptively learn spatial hierarchies of features from input images. Convolutional layers, pooling layers, and fully connected layers make up the three key components of CNNs. The convolutional layers apply a convolution operation to the input, preserving the relationship between pixels by learning image features using small squares of input data. Pooling layers reduce the dimensions of the data by combining the outputs of neuron clusters into a single neuron in the next layer, which makes the network invariant to the scale and orientation of the input. These features make CNNs particularly well suited for tasks involving images, such as object and face recognition. An advanced type of neural network that has gained prominence for its ability to integrate unordered data into a known representation is the autoencoder. An autoencoder is designed to learn efficient representations, encodings, for a set of data, typically for the purpose of dimensionality reduction or feature learning. It consists of an encoder network that compresses the input into a latent space representation, and a decoder network that reconstructs the input from this representation. Autoencoders are unsupervised learning models that can learn to copy their inputs to their outputs. They are used for tasks such as anomaly detection, where they can identify instances that do not conform to an expected pattern in the data. Apart from these main types, other architectures include generative adversarial networks, GANs, which consist of two networks that are trained simultaneously by a system of competing gradients, a generator that creates images from noise, and a discriminator that learns to distinguish between genuine and artificial images. The training process involves a game-like scenario where the generator tries to produce data that is indistinguishable from real data, while the discriminator tries to get better at distinguishing fake data from real data. This type of network is responsible for the creation of highly realistic synthetic images and is also being used in novel applications such as drug discovery. The neural network landscape is also populated by a multitude of hybrid models that blend the strengths of different architectures to address specific challenges. For instance, CNNs are often combined with RNNs for tasks like video recognition or scene labeling, where both image features and temporal dependencies must be understood and considered. Other hybrids include convolutional LSTM networks, which bring together the spatial hierarchy inherent in CNNs with the sequence recognition capabilities of LSTMs, making them ideal for tasks like predicting precipitation in weather models or recognizing gestures in video data. Specialized networks also exist for specific domains. Graph neural networks, GNNs, are designed to process data that is represented graphically. This allows them to consider the connections between data points, nodes, and their relationships, edges. GNNs are used in a wide range of applications including social network analysis, molecule structure analysis, and recommendation systems. These exemplify how domain-specific challenges drive the innovation of specialized neural network architectures tailored to the intricacies of the data involved. In addition, attention mechanisms have been introduced to neural networks to improve performance on tasks that require focus on specific parts of the input data. Attention allows the network to dynamically concentrate on the most relevant parts of the input to make better predictions or generate more coherent sequences. Transformer networks, which rely solely on attention mechanisms without any recurrence, have set new standards in natural language processing tasks, showcasing the immense potential of neural networks when architected with a keen understanding of the task at hand. The field of neural networks is evolving rapidly. While the types of neural networks mentioned here represent some of the most well-known and commonly used architectures, new variations and novel approaches are continuously emerging as researchers strive to improve performance and extend the applicability of neural networks to an ever-growing range of tasks. These expansions reflect the dynamic nature of the field, with constant innovation and reevaluation of methods to address the computational and representational challenges posed by different kinds of data and problem domains. The exploration of neural network types provides a glimpse into the complexity and diversity of approaches that exist within the field of artificial neural networks. Each type is a tool fashioned to tackle specific types of problems, and understanding their differences and applications is crucial for both researchers and practitioners. Advances in this field will undoubtedly introduce new architectures that will expand the horizons of what is possible with neural networks, further unlocking their potential to mimic and exceed human-like pattern recognition and decision-making capabilities. 1.4 Basic Components: Neurons and Synapses. Neural networks, in the context of machine learning, are computational models inspired by the biological neural networks that constitute animal brains. At the heart of these models lie artificial neurons, also known as nodes or units, which are designed to mimic the properties of biological neurons. An artificial neuron receives one or more inputs, processes them, and generates an output. The neuron's functionality is rooted in its ability to weigh its inputs, sum them up, and pass the sum through a nonlinear function known as an activation function. This behavior is akin to the way biological neurons process signals received from dendrites and generate an output that travels along the axon. Each artificial neuron is connected to others by means of structures analogous to biological synapses, which in the realm of machine learning are referred to as weights or parameters. These weights determine the strength and direction, inhibitory or excitatory, of the connection between neurons in the network. During the training phase, these weights are adjusted through a process called learning, which involves optimizing the weights so that the neural network can perform a specific task with increasing accuracy. The optimization is typically achieved by using algorithms, such as gradient descent, along with backpropagation, which allows the network to propagate errors backwards and adjust the weights accordingly. The simplest model of an artificial neuron is the perceptron, originally introduced in the 1950s. It consists of input values, weights, a bias term, a weighted sum of the inputs, and an activation function. The perceptron receives multiple input signals, multiplies each input signal by its corresponding weight, and then sums them together. The resulting value is then modified by a bias term, akin to adjusting the threshold at which the neuron activates, and is finally passed through an activation function. The activation function's purpose is to introduce nonlinearity into the output of the neuron, a feature crucial for enabling the neural network to learn and model complex patterns. The activation functions play an essential role in neural networks because they decide whether a neuron should be activated or not. There are different types of activation functions used in practice, including but not limited to the sigmoid, hyperbolic tangent, and rectified linear unit (ReLU) functions. The sigmoid function, for instance, outputs a value between 0 and 1, making it useful for models where we need to predict probabilities. The hyperbolic tangent function, or tanh, outputs values between -1 and 1, which can be advantageous by centering the data and can lead to faster convergence during training. Meanwhile, the ReLU function, which gives an output of 0 for negative inputs and a linear output for positive values, is widely used because of its computational efficiency and ability to mitigate the vanishing gradient problem. The overall behavior of a neural network emerges from the collective operation of its individual neurons and the intricate web of synapses joining them. A single-layer neural network, or a single perceptron, can only model linearly separable functions, which limits its capacity to solve more complex problems. The arrangement of neurons into layers, with multiple neurons in each layer, and establishing connections between these layers is a significant advance that leads to the concept of multi-layer perceptrons, MLPs. These networks are composed of an input layer, one or more hidden layers, and an output layer. MLPs are capable of modeling more complex functions by composing multiple linearities and non-linearities, enabling them to learn from a broad range of data. Within multi-layer networks, the hidden layers play a pivotal role. They are not directly exposed to the inputs or outputs, but they capture and transform the underlying structure of the data. Each neuron in the hidden layers can be thought of as learning to recognize specific features or patterns from the inputs it receives. As data flows through the network, it gets transformed layer by layer, with each subsequent layer potentially learning to recognize more abstract features or concepts. This hierarchical learning is part of what gives neural networks their power, allowing them to perform well on tasks such as image and speech recognition, where higher levels of abstraction are essential. The synapses or weights encapsulate the knowledge that the neural network acquires during training. Each weight adjustment is a small step in the multidimensional space of the network's parameters. The ultimate goal is to find the optimal set of parameters that minimizes the difference between the network's predictions and the true outputs. The loss function is a critical component that quantifies the cost or error of predictions. Common loss functions include mean-squared error for regression tasks or cross-entropy loss for classification tasks. The choice of a loss function is guided by the particular application and the desired properties of the neural network. Training neural networks usually involves providing a large set of labeled data, which the network uses to learn from by continuously adjusting its weights. This process of adjustment is iterative and can be quite computationally intensive, depending on the complexity of the network and the size of the data set. As the network iteratively learns from the training data, it attempts to generalize from the examples provided to it, ultimately aiming to make accurate predictions or decisions when faced with new, unseen data. Ensuring that a neural network generalizes well to new data is one of the crucial challenges in machine learning. Overfitting, where the network learns the training data too well, including its noise and outliers, is a common problem that can lead to poor performance on new data. Techniques such as regularization, dropout, and early stopping are employed to mitigate this risk. Understanding the fundamental operations of neurons and synapses in a neural network lays the foundation for exploring more advanced concepts, such as convolutional neural networks, CNNs, and recurrent neural networks, RNNs, which are tailored for specific types of data and tasks. CNNs, for example, are designed to process grid-like data such as images. They employ filters that capture local patterns such as edges and textures, making them extremely effective for tasks involving visual recognition. RNNs, on the other hand, have internal memory that allows them to process sequences of data, such as time series or language, rendering them suitable for tasks like speech recognition or machine translation. The current state of neural networks is a result of continual refinements and innovations that build upon these basic components. Researchers have proposed various novel architectures, learning algorithms, and training techniques to improve the performance and efficiency of neural networks. Democratization of machine learning through open-source software and improvement in computational hardware, such as graphics processing units, GPUs, and tensor processing units, TPUs, have significantly accelerated the research and application of neural networks in numerous fields. With the basic understanding of neurons and synapses, one can appreciate how simple mathematical constructs can be scaled up to create systems capable of performing tasks that once seemed exclusive to human intelligence. This foundational knowledge is essential for diving deeper into the more nuanced aspects of neural network design and application. 1.5 Activation functions explained. Activation functions in neural networks play a critical role in determining the output of a neural node given a set of inputs, weights, and biases. They are functions that take the input signal and produce an output signal, but they take into consideration the threshold or complexity of the input. Their primary purpose is to introduce nonlinearity into the output of a neuron. This is essential because most real-world data is nonlinear, making linear models insufficient in handling such complexities. The choice of an activation function significantly impacts not only the capability of the neural network to learn complex patterns, but also the speed at which it learns. Some commonly used activation functions include the sigmoid, 10H, ReLU, rectified linear unit, leaky ReLU, and softmax. Each of these activation functions has its characteristics and is selected based on the specific requirements of the neural network model being developed. The sigmoid activation function is one of the earliest used in neural networks. It has the form of an S-shaped curve and is defined mathematically by the equation fx equals 1 plus express x, where x is the input to the function. The sigmoid function outputs values in the range between 0 and 1. This makes it a good choice for binary classification problems. However, its usage has declined with the introduction of other functions due to the vanishing gradient problem, where the gradient becomes too small, slowing down the learning process. The hyperbolic tangent function, or 10H, is similar in shape to the sigmoid, but outputs values in the range between -1 and 1. Like the sigmoid, it is nonlinear and can handle two-class classification problems well. Its advantage over the sigmoid is that negative inputs will be mapped strongly negative, and the zero inputs will be near zero in the output. This helps the model learn faster and make decisions without bias to only one side of the chosen range. The ReLU function addresses some of the issues found with the sigmoid and 10H functions, mainly by solving the vanishing gradient problem. ReLU is defined as fx equals max 0x, meaning it outputs the input directly if it is positive, otherwise it will output 0. It has become a default activation function for many types of neural networks because it allows models to converge faster and mitigates the gradient vanishing problem through its linear, non-saturating form. Yet, ReLU functions are not without their problems. They can suffer from what's known as dying ReLU syndrome. This occurs when inputs to ReLU result in negative values, and the gradients for these neurons become 0. These neurons stop contributing to the learning process, effectively dying. To overcome this, variations like leaky ReLU, which allows a small, non-zero gradient when the unit is not active, have been introduced. The softmax function is a generalization of the sigmoid function that is used in multi-class classification problems. It can be understood as a probability distribution across different outcomes. The softmax function calculates the exponential of each input value, normalizes these values by dividing each by the sum of all exponentials, resulting in an output that represents the probability distribution across a list of potential outcomes. When designing a neural network, one must be careful in the choice of the activation function, as it affects both the efficiency and the capabilities of the network. A poorly chosen activation function can hinder the network's ability to learn from the training data, while a well-chosen function can enhance its performance, reduce the time needed to train, and achieve better overall results. Advanced neural network models often employ different activation functions in different layers depending on the task that particular layer is aimed at performing. For example, ReLU might be used in the hidden layers for its efficiency, while softmax is applied in the output layer of a classifier to interpret the outputs as probabilities. Activation functions also play a significant part in the backpropagation process since their derivatives are used to update weights and biases. This is an integral aspect, as the derivative of the activation function determines how the gradient descent algorithm will behave, whether it will converge smoothly or oscillate. Understanding the range and behavior of different activation functions is vital in setting the initial weights. If the range is not considered, it can lead to issues such as all neurons firing in an uncontrolled manner or none firing at all. Therefore, the initial weights are usually set to small values to keep the outputs of the activation functions in their linear regions, where they are sensitive to changes in the input. It's worth mentioning that novel activation functions continue to be researched and developed. Variants inspired by biological processes or tailored to specific types of neural networks keep emerging in literature. Researchers are continuously exploring the development of adaptive activation functions, which change their behavior during training to better suit the characteristics of the data. In conclusion, activation functions are a fundamental part of neural network architecture, directly affecting their performance and effectiveness. Understanding the various types of activation functions and their appropriate application is essential for anyone looking to delve into neural network design or engage with deep learning technologies. 1.6 Network Architectures, Feedforward and Feedback. The understanding of neural network architectures is pivotal when delving into the study of artificial neural networks. Primarily, neural networks can be classified based on the flow of information within their structure. This classification leads to two main types of network architectures: feed-forward neural networks and feedback or recurrent neural networks. Feed-forward neural networks are the simplest type of artificial neural network wherein connections between the units do not form a cycle. On the other hand, feedback neural networks are characterized by the presence of cyclical paths which allow for the persistence of information and hence a form of memory. Feed-forward neural networks consist of an input layer, one or more hidden layers, and an output layer. The input layer receives the initial data that is to be processed. This data then propagates forward through one or multiple hidden layers where further computation occurs through a series of weighted connections and activation functions. Each of the neurons in these layers represents a mathematical function, and the design of these functions and their interconnectivity defines the network's ability to learn complex patterns. The final processed information is then outputted through an output layer. This architecture is suitable for a range of applications, including classification, regression, and even more complex tasks such as image and speech recognition. One of the primary advantages of feed-forward networks is their simplicity and the ease with which they can be analyzed and understood. This straightforward structure facilitates efficient training protocols such as backpropagation, where errors from the output are propagated backwards to adjust the network weights. These adjustments are made iteratively during the training phase to minimize the difference between the actual output and the desired output. However, this simplicity comes with the limitation that feed-forward networks do not naturally handle sequential or temporal data, where the current output is dependent on previous inputs or computations. Contrarily, feedback neural networks, also known as recurrent neural networks (RNNs), are capable of processing data with sequential and temporal dependencies. Recurrent networks have connections that feed back into themselves, either directly or indirectly, enabling them to maintain a memory of previous inputs within their internal state. This is achieved by allowing neurons to send feedback signals to other neurons. As a result, the output of a recurrent neural network is influenced not only by the current input to the network, but also by what has been learned from previous inputs. The maintenance of state allows RNNs to exhibit dynamic temporal behavior and makes them particularly well suited for tasks that involve sequential data, such as natural language processing, time series prediction, and generative models. The ability to remember previous inputs means that the network takes into account the context of an input sequence, which is a crucial aspect in many real-world applications. The training of RNNs, however, can be significantly more complex than that of feed-forward networks, largely due to difficulties like the vanishing gradient problem, which can make learning long-term dependencies challenging. Despite their potential, the traditional forms of RNNs have limitations in learning long-range temporal dependencies due to issues related to computational complexities, such as the exploding or vanishing gradient problems. To address these challenges, more advanced forms of recurrent neural networks have been developed. Long short-term memory networks, LSTMs, and gated recurrent units, GRUs, are variations of RNNs that are designed to better capture long-term dependencies. These networks incorporate mechanisms called gates that regulate the flow of information, allowing them to retain or forget information over long sequences, thereby mitigating the traditional problems faced by simple RNNs. While feed-forward and feedback architectures can be viewed as opposites, they are sometimes combined in practice to exploit the strengths of both. For instance, a recurrent network might process sequential data to capture temporal information, which is then fed into a feed-forward network for classification purposes. This hybrid approach can enhance performance in complex tasks that require the network to understand both the temporal dynamics of the input data and to make accurate predictions or classifications based on that data. In the realm of deep learning, where networks comprise multiple layers of neurons, both feed-forward and feedback architectures have been expanded into deeper and more sophisticated structures. Deep feed-forward networks, also known as deep neural networks, DNNs, have many hidden layers that allow for higher levels of abstraction and complexity in learning representations. Deep recurrent neural networks, similarly, add depth to the recurrent connections, enabling nuanced hierarchical temporal behaviors. Selecting the right architecture for a given task is critical to the success of a neural network application. The choice between a feed-forward and a feedback architecture, as well as determining the appropriate complexity and depth of the network, depends on the specific characteristics and requirements of the task at hand. Real-world problems often dictate the architecture and the parameters that should be employed, underscoring the importance of an extensive understanding of both network types and their suitability for various applications. To summarize, feed-forward and feedback networks form the foundational architectures upon which neural network research and application are based. Each architecture has its own advantages and limitations, which must be considered when developing and deploying neural network solutions. The computational efficiency and simplicity of feed-forward networks stand in contrast to the dynamism and temporal sensitivity of feedback networks. With ongoing advancements in neural network research, the boundaries of these architectures are continually expanding, allowing for more complex and capable systems that push the envelope of what artificial intelligence can accomplish. 1.7 Training neural networks. An overview. Training neural networks is a process centered around the improvement of a network's ability to make predictions or decisions without being explicitly programmed to perform the task. It involves feeding the network with a large amount of data, adjusting its parameters, and incrementally improving its performance. This process generally follows a cyclical pattern that includes forwarding propagation of inputs through the network to generate an output, comparing this output with the desired outcome, and using this comparison to inform adjustments to the internal parameters. These steps contribute to the network's learning from its errors, becoming better attuned to the nuances within the data over time. The depth and complexity of training are determined by both the architecture of the neural network and the characteristics of the data it processes. A key component of training is the cost function, which measures the difference between the actual output of the network and the expected target value. This function is essential because it quantifies the error or loss that the network needs to minimize through training. By employing optimization algorithms such as gradient descent, the training process iteratively adjusts the weights and biases within the network to reduce this cost, thus enhancing the neural network's predictive accuracy. One of the most crucial concepts in training neural networks is backpropagation. Backpropagation is the algorithm responsible for calculating the gradient of the network's loss function with respect to each weight in the network. By understanding how each weight contributes to the error, backpropagation efficiently identifies the direction and magnitude by which weights need to be modified to reduce the overall loss. This backward flow of error correction from output to input is key in enabling deep neural networks, with their many layers, to learn complex representations of data. Neural network training also requires a thoughtful approach to data preparation. The dataset must be divided into at least two subsets, one for training and another for validation. Sometimes a third set, known as the test set, is used to evaluate the network's performance after training is complete. This separation is critical as it prevents overfitting, where the network performs well on the training data, but fails to generalize to new, unseen data. Properly partitioning the data ensures that the network is robust and performs well in practical applications outside the training environment. Hyperparameter tuning is an essential part of the training process that involves setting the configuration of the neural network model, such as the learning rate, batch size, and the number of epochs. These hyperparameters are not directly learned from the data, but are selected before the training begins. They have a significant impact on the training process and the ultimate performance of the network. Experimentation and experience are often required to choose optimal hyperparameter values, and advanced techniques such as grid search or random search are used to automate and systematize this process. One critical aspect often overlooked in the training of neural networks is the need for regularization to combat overfitting. Overfitting occurs when a model learns the training data too well, including its noise and outliers, thereby losing the ability to generalize to new data. Techniques such as dropout, where randomly selected neurons are ignored during training, or L2 regularization, which adds a penalty for larger weights, help the network to focus on the more prominent patterns in the data, leading to improved generalization. The availability and quality of data play a substantial role in the training of neural networks. In supervised learning, where the network is trained with labeled data, having a diverse and representative collection of examples is crucial for the model to learn effectively. Conversely, in unsupervised learning, the challenge lies in discerning structure within labeled data, which the neural network can learn to represent in a meaningful way. Semi-supervised and reinforcement learning constitute other paradigms where the network is trained with limited labeled data or through interactions with an environment, respectively. The computational power required to train neural networks, especially deep networks, cannot be understated. Training involves multiple forward and backward passes through layers of the network, which is resource-intensive. This requirement has been partially alleviated with the advent of specialized hardware like graphics processing units, GPUs, and tensor processing units, TPUs, which are designed to handle the parallel computations neural network training requires. Cloud-based platforms also provide scalable resources for training complex networks. Advancements in neural network training methodologies continue to emerge as research in the field deepens. Transfer learning, for example, allows for the utilization of pre-trained models on new tasks with only minimal additional training. This approach leverages the knowledge that a model has already acquired, reducing the training time and data requirements for new tasks. Similarly, recent developments in few-shot learning and zero-shot learning suggest that neural networks may eventually require even less data to make accurate inferences. Recognizing when a neural network is adequately trained is as important as the training process itself. The concept of convergence in the context of neural networks refers to the point where further training does not significantly decrease the loss function. Determining convergence is not always straightforward and requires careful monitoring of the loss function's trajectory and the validation set's performance. Early stopping is a technique often used to halt training when the validation loss stops improving, preventing both overfitting and unnecessary computational expenditure. 1.8 Cost functions and optimization. In the field of neural networks, a cost function, also known as a loss function or objective function, is a fundamental concept that quantifies the difference between the expected outcomes and the outputs produced by the neural network. It acts as a guide for the learning algorithm, providing a way to measure how well the neural network is performing. As the network learns from data, the aim is to minimize the value of the cost function. This process of minimizing the cost is referred to as optimization. Optimization is a key process in training neural networks, and various techniques can be employed to achieve this goal. Gradient descent is one such technique, and it plays an integral role in neural network training. It uses the gradient of the cost function to determine the direction in which the weights of the network should be updated, so that the cost function's value decreases. The gradient is essentially a vector consisting of the partial derivatives of the cost function with respect to each weight in the network. The cost function's landscape can be complex, with multiple local minima, and possibly a global minimum, which is the point where the function reaches its lowest possible value. In high-dimensional spaces, where neural networks often operate, local minima can pose a significant challenge. Optimization algorithms strive to reach the global minimum, but they can also get stalled in local minima. Advanced optimization techniques, like momentum and adaptive learning rates, are designed to help navigate the cost function landscape more effectively and avoid getting trapped in local minima. There are various types of cost functions used in neural network training, and the choice of which to use depends on the specific problem being addressed. The mean squared error (MSE) function, for instance, is commonly used for regression tasks, where the goal is to predict continuous values. The MSE calculates the average squared difference between the predicted values and the actual values, and the neural network aims to minimize this value. On the other hand, classification tasks often employ the cross-entropy cost function, which measures the performance of a classification model whose output is a probability between 0 and 1. Another aspect of cost functions and optimization is the concept of overfitting, which occurs when a neural network learns to perform very well on the training data, but fails to generalize this performance to unseen data. Regularization techniques, such as L1 or L2 regularization, are employed to prevent overfitting. They work by adding a penalty term to the cost function, which constrains the magnitude of the network weights and encourages the network to learn more generalized features that are robust against variations in data. Batch and mini-batch training are strategies used to address scenarios where the training dataset is large. In batch training, the cost function is evaluated over the entire training dataset before the weights are updated, a process that can be computationally expensive and time-consuming. In contrast, mini-batch training subdivides the data into smaller sets, allowing for more frequent updates of the weights. This method can result in faster convergence and makes better use of computational resources. The learning rate is a critical hyperparameter in the optimization process. It defines the size of the steps taken in the weight update process during training. If the learning rate is too high, the optimization algorithm might overshoot the minimum of the cost function and fail to converge. If it is too low, the learning process will be slow and can get stuck in local minima. Adaptive learning rate algorithms, such as ADAM and RMS-PROP, mitigate these risks by adjusting the learning rate as training progresses. The role of data normalization and feature scaling is also important in the optimization process. Input features need to be on a similar scale for the gradient descent algorithm to function efficiently. If the scales are dissimilar, it can distort the shape of the cost function landscape and make it more challenging for the optimization algorithm to find the minimum. Weights initialization is crucial for successful optimization in neural networks. Poor initialization can lead to slow convergence, or the optimization process might not converge at all. Strategies for weight initialization have been developed, such as Xavier and He initialization, which adjust the weights based on the size of the networks to improve the likelihood of successful learning. The correct choice of weight initialization can significantly influence the effectiveness of the optimization process. In the development of neural network architectures, complexities arise with the introduction of new layers and more parameters. Deep learning involves training neural networks with many layers, which can significantly increase the number of local minima in the cost function landscape. This introduces additional challenges for optimization algorithms. Techniques like dropout and batch normalization are used to manage these complexities and help ensure that deep neural networks can be trained effectively. Optimization in neural networks is an ongoing field of study, with researchers constantly proposing new algorithms and methodologies to enhance the training process. The interplay between various components of the optimization process, such as the cost function, optimization algorithm, learning rate, and regularization, underscores the complexity of training effective neural networks. The ultimate goal of optimization is to create neural networks that perform well not only on the training data, but also maintain their performance when confronted with new, unseen data, thereby achieving generalization. 1.9 Tools and Frameworks for Neural Network Development. The development of neural networks has been facilitated by a multitude of tools and frameworks designed to simplify the creation, training, and deployment of these complex systems. Each framework offers distinct features, advantages, and a level of abstraction appropriate for different use cases. One of the primary benefits of using a neural network framework is the abstraction of low-level mathematical operations, which allows researchers and developers to focus more on the architecture of the neural models and less on the underlying mechanics. Among the most prominent frameworks for neural network development is TensorFlow, an open-source library developed by the Google Brain team. TensorFlow provides a comprehensive ecosystem of tools, libraries, and community resources that assist developers in building and deploying machine learning applications. It supports a wide range of neural network architectures with its flexible computational graph, where nodes represent mathematical operations and edges symbolize multidimensional data arrays, tensors, that flow between them. Furthermore, TensorFlow's ability to leverage GPU acceleration significantly reduces training time for complex models. Another widely used framework is PyTorch, developed by Facebook's AI Research Lab. PyTorch is prized for its dynamic computational graph, which is constructed on the fly during execution and enables more intuitive coding of complex architectures. This feature makes PyTorch exceptionally well-suited for research and prototyping, as it allows for easy debugging and a more interactive development process. PyTorch also integrates with Python's robust ecosystem, making it accessible to a broad base of developers. Keras is a high-level neural networks API that can run on top of TensorFlow, CNTK, or Theno. It focuses on user-friendliness, modularity, and extensibility. By providing high-level building blocks for developing neural networks, Keras allows for the easy and fast prototyping of deep learning models. This framework is particularly advantageous for beginners due to its straightforward syntax and minimal learning curve, as well as for researchers interested in trying new ideas without delving into the complexity of lower-level operations. Caffe, a framework developed by the Berkeley Vision and Learning Center, is known for its speed and modularity. It is particularly well-suited for applications that require convolutional neural networks, and has been widely adopted in the domains of vision, speech, and multimedia. Caffe's expressive architecture encourages application and innovation, while its extensible code fosters active development. Although it might not provide the dynamic computational graph structure of PyTorch or the extensive ecosystem of TensorFlow, Caffe remains a strong option for certain types of projects. Microsoft's Cognitive Toolkit (CNTK) is another deep learning framework that offers both high performance and scalability. CNTK excels when it comes to handling massive datasets and can be run on multiple GPUs, making it a good choice for commercial-grade applications. Its efficient performance is attributed to its optimized computational graph and its ability to parallelize data and computations across available resources. However, CNTK's user base is comparatively smaller, which can impact the availability of community support and resources. Theno is a Python library that allows for the definition, optimization, and evaluation of mathematical expressions, especially ones involving multidimensional arrays. While it is no longer in active development, having been effectively succeeded by TensorFlow and PyTorch, Theno played an important role in the early days of deep learning frameworks. It established many of the core concepts that have since been adopted by other frameworks, such as automatic differentiation and optimization for GPU computation. MXNet, supported by Amazon Web Services (Oz), is designed for both efficiency and scalability, making it another suitable choice for developing and training deep neural networks. It blends imperative and symbolic programming to provide flexibility and efficiency. MXNet is capable of running on a wide variety of devices, from smartphones to distributed cloud infrastructure, which aligns with its goal of being a go-to framework for both research prototypes and production systems. Another tool of note is ONNX, Open Neural Network Exchange, which is not a framework but an open ecosystem for interchangeable AI models. ONNX provides a standard format for representing machine learning models, enabling them to be transferred between different frameworks with minimal friction. This is particularly relevant for developers who may need to use different frameworks during different stages of their project, such as rapid prototyping in one and efficient deployment in another. Deep learning frameworks are constantly evolving with new features, optimizations, and supporting libraries. To keep up with these developments, developers and researchers must continually update their knowledge and skills. Engaging with the community through forums, attending workshops, and contributing to open-source projects are effective ways to stay informed. Online resources, such as tutorials, documentation, and courses, are readily available and often endorsed by the organizations behind the frameworks. While several frameworks have been highlighted here, it is essential to understand that the choice of framework depends on the specific requirements of the project at hand. Each tool has its strengths and weaknesses, and the decision should be made based on factors including model complexity, ease of use, speed, support for multi-GPU training, and integration with other software systems. Exploring various options and benchmarking them against one's needs is a critical process in selecting the right tool for neural network development. Selecting the right framework or tool is just the beginning of neural network development. A successful project requires clear understanding of the problem domain, data pre-processing, network design, parameter tuning, training, and optimization. Tools can simplify or automate parts of this process, but the developer's expertise and experience often play a determining role in the success of the neural network model. As the field of machine learning continues to mature, these tools and frameworks will evolve, offering even more capabilities to facilitate the design and deployment of advanced neural network architectures. 1.10 Applications and Limitations of Early Neural Networks. The early neural networks, which originated in the latter half of the 20th century, paved the way for numerous advancements in the field of artificial intelligence, AI. These foundational networks, though primitive by today's standards, highlighted the potential for machines to perform tasks traditionally requiring human intuition and intelligence. Their applications ranged from basic pattern recognition to early forms of predictive modeling. For example, the perceptron, one of the earliest neural network models developed, was used for simple classification tasks, capable of resolving linearly separable data. It demonstrated the machine's capacity to learn from data and adjust its computations to improve accuracy over time. However, these networks had limitations, primarily due to their simplicity and computational constraints of the era. For instance, early networks had a limited number of layers and neurons, which restricted their capacity to model complex functions. This limitation was directly tied to the hardware available at the time, with processing power and memory insufficient to support larger, more intricate networks. Furthermore, these systems often suffered from the inability to solve nonlinear problems, a result of their straightforward architecture. They could not capture the complexity inherent in many real-world datasets, a function that modern deep neural networks can perform with greater proficiency. One of the key applications of early neural networks was in handwriting recognition. These networks were among the first to effectively demonstrate that machines could interpret and process visual data. Banks and postal services used early forms of neural networks to decipher handwritten numbers on checks and to sort mail by interpreting handwritten zip codes. While successful to a degree, these networks struggled with complex or unclear handwriting, revealing the model's need for clear, unambiguous data to function properly. Despite these challenges, the success in these domains showcased neural networks' potential, leading to increased research and development efforts in the field. There are other areas too where early neural networks found use. In industrial settings, they were employed for predictive maintenance by modeling machine operation and identifying patterns indicative of failure, thereby helping in preventing downtime. Their use in financial markets for predictive analysis, albeit limited, provided insights into potential future market behaviors based on historical data. These early forays into machine learning applications showed promise for the role of AI in decision-making processes and strategic planning across various sectors. While these networks' roles in applications were growing, they faced a significant challenge in the form of the XOR problem. This was a demonstration of their limitations in handling nonlinear separability, which many real-world problems entail. The perceptron could not solve problems where a linear decision boundary was not sufficient to distinguish between classes of data. This fundamental issue brought about a temporary waning in interest and funding for neural network research, known as the AI winter, during which progress in the field significantly slowed. In response to these limitations, researchers developed new architectures and learning algorithms. Notably, the introduction of backpropagation and multi-layer networks marked a significant advance. These methods allowed networks to adjust not only the final decision, but the internal representations in hidden layers as well. This led to a leap forward in the kinds of complexity neural networks could handle, although it still took several years for these improvements to overcome the skepticism caused by early failings. Early neural networks also made contributions to the field of pattern recognition and image processing beyond handwriting recognition. They were used to identify and classify simple images, demonstrating an ability to automate tasks which until then had relied on laborious human effort. With their capability to learn from examples rather than being explicitly programmed for each new image, they introduced a scalable approach to image classification. However, these systems were far from perfect, with accuracy significantly dependent on the variation and quality of the input data. As neural networks began to grow in ability and complexity, their applications expanded into natural language processing, NLP. Early attempts involved understanding and generating simple texts or phonetic patterns for speech recognition. While not nearly as competent as modern NLP systems, these attempts laid the groundwork by showing that neural networks could process sequence data and, in some cases, learn to parse basic syntax or semantics. But these early networks were still limited to relatively rigid, rule-based systems and struggled with the nuances and variability of human language. Further expanding the scope of neural networks, the 1980s saw the advent of recurrent neural networks, RNNs, designed to handle sequential data such as time series or spoken language. RNNs were a step change in that they could use their internal state to process sequences of inputs, which allowed them to produce outputs influenced by a combination of current and prior inputs. While revolutionary, RNNs in their early forms were difficult to train and suffered from problems like vanishing and exploding gradients, which made them unreliable for long sequences. The progress in the field of neural networks, together with their limitations, shaped the trajectory of AI research. It laid the foundation for modern deep learning, brought attention to the subtleties of machine learning, and underscored the importance of data quality and algorithmic complexity. Early neural networks were the progenitors of today's advanced AI systems, their applications providing a glimpse into what was possible, and their limitations setting the stage for the radical improvements we continue to witness. They stand as a testament to the methodical progress necessary to overcome the complexities of modeling intelligence. Their legacy is a reminder that the journey of AI has been one of incremental steps, each building upon the last, to achieve the sophisticated neural network architectures in use today.